Welcome to this explainer. If you've ever stared up at the night sky and wondered exactly how we manage and track the over 7,000 active satellites currently buzzing around our planet, well, you are absolutely in the right place. Today, we're decoding the secret language of data. We're going to break down the fundamental types of data using the high-stakes, incredibly precise world of space analysis. By the end of our time together, you won't just see data as a bunch of random numbers. You'll see it as the vital, structured foundation that keeps our modern satellite fleets functioning.
So it all starts with one massive question. How do we actually measure the cosmos? When you're managing a vast fleet of satellites zooming around the Earth at thousands of miles per hour, you aren't exactly looking through a telescope. You're looking at data streams. But here's the secret. Not all data is created equal. To effectively manage a satellite fleet, you absolutely have to decode specific types of foundational data. Because if you misunderstand the type of data you're looking at, you completely misunderstand the physical reality of what your spacecraft is actually doing.
Section 1. Decoding orbital data. Okay, our very first fundamental tool for understanding and monitoring spacecraft is numerical data. This is simply information expressed as numbers representing measurable or countable quantities. When you think of data, this is probably what immediately pops into your head, right? It's the quantitative stuff, the math, the raw figures that tell us exactly how fast, how hot, or how far away our orbital assets are. But numerical data isn't just one big, simple bucket.
Section 2. Numerical data, continuous versus discrete.
To successfully run a fleet, we have to master this distinction. On one side, we have continuous data, which is all about measuring. On the other side, we have discrete data, which is all about counting. The crucial point here is the difference between capturing a physical reality that can fluctuate and be broken down infinitely versus counting distinct whole objects. Basically, if you're using a tool to measure something, you're dealing with continuous data. But if you're using your finger to point and count things one by one, you're dealing with discrete data. Let's ground this in our orbital example to make it perfectly clear.
Take a look at this measurement, 24.582 degrees Celsius. A satellite in low Earth orbit goes from a blistering 120 degrees Celsius in direct sunlight down to negative 150 degrees in Earth's shadow. As it moves, its temperature fluctuates continuously. It passes through 24.1, 24.582, and literally every tiny fraction of a degree in between. This brilliantly illustrates what continuous data is all about. You're measuring a continuous physical state that can be captured to a practically infinite degree of precision. Now contrast that with a totally different kind of number, 42 satellites. The number of satellites in a fleet is completely different from our temperature reading. This is discrete data. Why? Well, because you can only count satellites in distinct whole numbers. I want you to imagine trying to launch or even count exactly half of a functional satellite. Actually, scratch that. If you have half a satellite, something has gone terribly wrong. You either have 42 satellites or you have 43. There is no 42.582. You're counting individual, separate entities.
Section 3. Categorical data. Orbit types.
So while numerical data relies on numbers and measurements, categorical data is all about descriptive groups. It groups things by qualitative traits. You aren't adding, subtracting, or averaging these categories. You're using them to sort your universe into distinct, manageable buckets based on shared characteristics. Now, what's really interesting here is how we can neatly divide these descriptive labels into LEO, or low Earth orbit, MEO, medium Earth orbit, and GEO, geosynchronous equatorial orbit. These aren't numbers we're doing math with, they're categorical buckets. If you want to know what environment a spacecraft is operating in, we group it into one of these qualitative labels. It's just an incredibly powerful way to organize non-numerical information across a vast fleet.
Section 4. Time series data.
Let's ground ourselves with a really clear definition here. Time series data is a sequence of data points collected or recorded at specific successive time intervals. This is where data truly comes alive. It's not just a single snapshot anymore, it's a moving picture. By recording the exact same metric over and over as the clock ticks forward, we can start to see patterns, behaviors, and rhythms in our satellite fleet that would be completely invisible if we only had a single isolated data point. Let's see exactly how this works in practice. So, step 1, we record an initial continuous data point, let's say our satellite's temperature. Then, step 2, we wait a specific interval, maybe 1 hour, and record it again. Step 3, we record it again another hour later. By step 4, we aren't just looking at a pile of random numbers. We're mapping a trend. We've taken individual continuous measurements and strung them together across time to create time series data. This allows us to see exactly how the satellite heats up and cools down as it moves along its orbit.
Section 5. Why data types matter.
Well, we've covered a lot of ground in this explainer today, from the supergranular measurements of heat to the broad categories of orbit types. But understanding these structural differences is the absolute baseline for any kind of accurate analysis. If you try to analyze categorical data as if it's continuous, your systems will straight up fail. And in space, failure is incredibly expensive. Knowing your data types is how you guarantee your tools actually match your reality. So let's lock this in. First, we have continuous data, which is all about measuring things with infinite precision, like our fluctuating satellite temperatures. Second is discrete data, which is counting whole distinct objects, like the exact number of satellites in our fleet. Third, categorical data, grouping things by descriptive traits, like assigning a satellite to LEO, MEO, or GEO. And finally, time series data, tracking any of those changes over successive intervals of time.
I want to leave you with a final thought to chew on. We just established that time series data allows us to map trends by tracking the past, right? But here's the ultimate question. If time series data tracks the past, can it predict the future of our orbits? Once you understand the structure of the data you're collecting today, you possess the very foundation needed to forecast what your satellites will do tomorrow. Keep exploring, keep questioning the data around you, and I hope this explainer has completely transformed how you view the numbers driving our universe.